Hello, Advanced Geometry. Mr. Donaldson here. Today we're going to start Chapter 2. Chapter 2 is all about reasoning. And we'll also learn a little bit more about some angle relationships and do some algebra application as well. But today's specific focus is on how we use inductive reasoning in life and in math. Alright, so here's a nice picture of my dog Neva. So Mr. Donaldson's dog, Neva, comes running when he says, "Neva, come." By using inductive reasoning, she knows if she comes, she'll get a treat. So, I have my dog trained. Well, if you ask Miss Butler, she'll tell you not very well. But Neva does know enough to when I say, "Hey, Neva, come," she'll come running over to me because she knows she's going to get a treat. And that is an example of inductive reasoning. Let's talk about why. So here's the process, all right? Here's the definition, rather. Inductive reasoning is the process of first observing data, 2, recognizing patterns with that data you've observed, and then 3, making a generalization about those patterns. So let's talk about Neva for a minute. What's the data she observed? She observed all these different circumstances when I called her over and she came to me and I gave her a treat. That's the data she's observed. She's making these observations like, "Oh, he gave me a treat when I came over. Oh, he gave me a treat when I came over." And then in her head she recognized a pattern. She goes, every time he calls me over, I get a treat. So then she made a generalization. And she says, "You know what? Every time he calls me over, I'm going to get a treat." So then she comes every time looking for that treat. That is an example of inductive reasoning. Now, a conjecture, this is mathematical language that we'll use throughout the course. This is when you come up with an idea. So when you use inductive reasoning to make a generalization, the generalization is called a conjecture. So if we go back to Neva, her conjecture was, every time he calls me and I go to him, I'm going to get a treat. That is her conjecture that she has made using inductive reasoning. All right, let's watch a little video clip of inductive reasoning in action here. This is from The Simpsons. You guys might be Simpson fans. Here we go.
I propose to determine the answer to the question, is my brother dumber than a hamster? Hey, Lise, look what I can do. Oh. Got it. Stupid bugs. Hey, a cupcake. Hamster 1, Bart 0. Experiment 2. The food is connected to a mild electrical current. The hamster has learned a valuable lesson. Beware the hand of man. Wise guy, eh? Ow! 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 Hamster 2, Bart 0. Bart, could you go get the cupcakes? Cupcakes. Yes, sweet cakes for all.
All right, so you can see, hopefully you noticed based on the discussion we're already having, you can see inductive reasoning at work. Let's talk about why. Each of Bart's interactions with the cupcakes was him observing data. So, the first time when he saw the cupcake and climbed up the bookshelf, that was a data point. The second time there when he was reaching for the cupcake and he got shocked, that was the data that he was observing. As his negative experiences with cupcakes continued, he began to recognize a pattern. He probably began to think in his head like, "Oh man, cupcakes are bad news," right? As a consequence of his data observation and recognizing the pattern, he was able to make the generalization that cupcakes would harm him. So he bugged out in that final scene, and he's like, "I want nothing to do with cupcakes," and then fell to the floor. So there you have it, folks. That, in a nutshell, like big picture, is inductive reasoning. So how does this relate to math? Well, you guys, in math, you use inductive reasoning all the time. You probably don't think about it as inductive reasoning, but you're always looking at a little piece of information and recognizing patterns and trying to figure out what to do next. And these, like fill in the blank for sequence problems, are a really good example of that. All right, so we'll walk through the inductive process here. So we want to use inductive reasoning to determine which numbers come next in each sequence. So here are the data points. We got a 1, we got a 5, we got a 9, we got a 13. They're all in order like that, so we need to take in consideration the different values of each of these data points and the order that they're in. So that's step 1. We observe the data. Step 2, we're going to look at patterns in this data. So here we go. Let's see. From 1 to 5, then I go from 5 to 9, then from 9 to 13. And you probably recognize there's a little bit of a pattern there. And each time you think, hey, you know what? I'm adding 4 each time. So inductively, you observe the data. You recognized a pattern. And next, you're going to make a conjecture. And that conjecture is, you know what? I think this sequence follows the rule that all you got to do is add 4 each time. Well, if you add 4 more, you get 17. And if you add 4 more to that, you get 21. So there you have it. That's simple mathematical application of inductive reasoning. All right. So the next example, right? This one, a little bit more to it. It's not just simply adding something, but let's go ahead and observe the data. So we got a -1, and then a 2, and then a -4, and then an 8. And when you guys with some good number sense, you probably recognize there's a pattern there. And you'll notice one thing is that the signs keep switching. It was negative, then positive, then negative, then positive. And you'll also notice if you disregard the signs, the numbers themselves just keep doubling. 1, and then 2, and then 4, and then 8. So you could just say, okay, the signs are going to alternate, and then you double the numbers. But you guys, that is exactly the same thing as simply multiplying by -2. So if I multiply by -2, a negative times a negative will give you a +2. If I multiply by, instead of x, I'm going to use a little symbol. If I multiply by -2 again, a positive times a negative is a -4. And if I multiply by -2 again, a negative times a negative is a +8. So if I continue that process to multiply by -2 again, I would end up with a -16. And then if I multiplied by -2 again, I would end up with a +32. So there you have it. We observed the data, we recognized a pattern, and we made a conjecture. Here's my conjecture for this one. You know what? I think I just add 4 each time. Here's a conjecture for this one. You know what? I think I'm going to multiply by 2 each time. And then we followed through with those conjectures. So here's another example. Okay, this is a little bit more geometric rather than what we were just talking about with sequences and lists of numbers. So use inductive reasoning to determine what figure would come next. So just thinking about it. So you guys notice that they're all polygons. Okay, let's observe some data. We got ourselves a 3-sided polygon or a triangle. Then we got a 4-sided polygon or a quadrilateral. Then a 5-sided polygon or pentagon. Then a 6-sided polygon or hexagon. So what you notice is that they're all polygons, and what's changing is just simply the number of sides it has. So we had 3 sides, and 4 sides, and 5 sides, and then 6 sides. So you guys are all pretty smart, and you could probably assume what would be next would be a heptagon or a 7-sided polygon. And notice that these aren't indicated to be regular. They're not indicated to be equilateral or equiangular. So it looks to me, based on the pattern or the data that I've seen, I could just draw any old heptagon. So there's 3, 4, 5, 6, 7-sided polygon. I got myself a heptagon. So there you go. Draw a heptagon and you'd be good to go. So again, we observed the data. We looked at all the, okay, we got polygons. They're increasing by 1 each time. So we saw the pattern there. It's increasing by 1 side each time. And then our conjecture. You know what? This is just simply a list of polygons. Each time the number of sides it has increases. So boom. So then, of course, the next one will be an octagon, and then a nonagon, then a decagon, etc. Does inductive reasoning always work? Inductive reasoning doesn't always work. And sometimes your conjecture may be false. To determine if your conjecture is false, all you got to do is try to find one single counterexample that contradicts your conjecture. All right? There's an example of this in problem 23 in the 2.1 assignment, when you kind of look for a counterexample to an inductive reasoning situation. One just like really easy example, so I can kind of tell you what a counterexample is, will be like, suppose every single day you guys came to my little virtual classroom, and every single day I was wearing a hat, right? Which I think's been true so far. So you guys show up and you say, oh, Mr. Donaldson's wearing a hat. And the next day, oh, Mr. Donaldson's wearing a hat. The next day, oh, Mr. Donaldson's wearing a hat. So you observe a pattern then based on all that data. And then you make a conjecture. Your conjecture is, you know what? Mr. Donaldson wears a hat every day. But then the next day you come to class, uh-oh, I'm not wearing a hat. That is a counterexample to your conjecture that I always wear a hat. So therefore your conjecture would be false. It just takes one counterexample to prove your conjecture is false. And we'll finish up by going back to Neva, because poor Neva has realized that her conjecture is false as well. Sometimes when Mr. Donaldson says, Neva, come, she inductively thinks, yes, I'm going to go get a treat. But occasionally Mr. Donaldson runs out of treats, and her conjecture of, if I go, I'll get a treat is proven wrong with a counterexample of not getting that treat. Poor little Neva, disappointed that her conjecture is false. But you know what? The next time we go out, she's going to hope her conjecture holds true. She wants that treat. So thank you guys. Hope that made sense. Good luck on your assignment.